Welcome to the Deep Dive. We're continuing our series looking into some really fascinating sequences from the online encyclopedia of integer sequences.
That's right. Today it's A000244. And, well, it looks pretty straightforward at first glance, just a list of numbers.
Yeah, seems simple.
But it's actually, a thread that connects some surprisingly deep and diverse parts of mathematics.
Okay, so we're talking about the powers of 3. 1, 3, 9, 27, 81, and, well, it keeps going.
Exactly.
And for this deep dive, we've pulled together quite a mix of some fun examples from number theory forums, articles on number bases, powers, and obviously the OEIS entry itself.
Yeah, and the goal here isn't just to list the numbers, right? We want to explore why they show up so much. What's so fundamental about powers of 3?
Right, what makes them tick? Okay, so basics first. The sequence is just numbers of the form 3 to the power of n.
Where n is a non-negative integer. So 3 to the 0 is 1, 3 to the 1 is 3, 3 squared is 9.
Got it. Pretty simple start.
And there's a recursive way, too, right? You start with 1, and then the next number is just, well, 3 times the previous one.
an equal 2 times an 1. Simple rule.
Simple rule, but as we'll see, a really powerful sequence.
Okay, so where does this fundamental nature first show up? I guess number systems.
Exactly. The ternary system, or base 3, that's the core connection.
Just like powers of 10 are the backbone of our decimal system, and powers of 2 for binary.
Powers of 3 are the place values for base 3. So 1, 3, 9, 27. Those are your columns, essentially.
So if I see, say, 121 in base 3, that's 1, 9, 2 3s, and 1, 1.
Precisely. 1 times 3 squared plus 2 times 3 to the 1 plus 1 times 3 to the 0.
Which is 9 plus 6 plus 1.16 in base 10.
Yep. And standard base 3 uses digits 0, 1, and 2. But one of the sources mentioned something really neat called balanced ternary.
Oh, yeah? What's that?
It uses digits -1, 0, and +1. It's apparently quite elegant for handling positive and negative numbers without needing a separate sign bit, which is interesting.
Huh, okay. And I read something about base 3 being surprisingly efficient.
It is. It comes down to this concept called radix economy. It's basically a measure of how efficiently a base represents numbers.
How do you measure that?
Well, roughly, you multiply the base by the number of digits needed for a large number. And mathematically, the absolute best base, the most compact, is actually e.
The natural log base, like 2.718.
That's the one. But obviously, e isn't an integer, so you can't really use it as a practical base.
Right, so which integer base is closest?
3. Base 3 actually has the lowest, meaning best, radix economy among all the integer bases.
Lower than binary.
Yes. There was a good example in the sources, representing 100,000. In base 10, that's 6 digits. 10 times 6 gives a score of 60.
Okay.
In binary, it takes 17 digits, so 2 times 17 is 34, better than decimal.
Right.
But in base 3, it only needs 11 digits, and 3 times 11 is 33. Just slightly better than binary for that number, but the difference grows for larger numbers.
Wow, that's genuinely counterintuitive. I would assume binary with fewer digits needed than decimal would be the most efficient overall.
It's that trade-off, isn't it, between how many digits you need and the sort of information capacity of each digit determined by the base.
Exactly.
And it's not just representation. Ternary logic has potential advantages, too.
How so?
Well, think about comparisons. Base 3 has 3 states, right? You could think of them as less, equal, greater, or maybe militia 1, 0, plus 1.
Okay.
So a single ternary operation could potentially compare 2 things and give you one of those 3 outcomes directly.
Whereas binary, with only 0 and 1, true or false,
Needs more steps. You'd need at least 2 comparisons maybe to figure out if something is less than, equal to, or greater than something else.
So if base 3 is so efficient, theoretically, why did binary completely take over computing?
Practicality, mostly. Building reliable electronic switches, transistors, really, that have 3 distinct stable states is just much harder than building ones with 2 states, on or off.
The engineering reality.
Exactly. There were early attempts, though, like Thomas Fowler's mechanical calculator back in the 1840s that used ternary principles.
Wow, that early.
And more famously, maybe, the Soviet CETON computer in the late 1950s. It was a fully functional ternary computer, quite advanced for its time, actually.
I think I read about the CETON. Fascinating bit of forgotten tech.
Absolutely. But, binary components were easier to mass produce and became the standard. The momentum just built behind binary.
Convention won out.
Pretty much. But the theoretical ideas haven't died. Some modern research, especially in things like cybersecurity or fault-tolerant computing, still looks at ternary systems. The extra state might offer advantages for error detection and correction, for example.
Interesting. Okay, what about representing fractions in base 3?
Well, just like base 10 struggles with 13, giving 0.333, base 3 handles fractions with powers of 3 in the denominator really cleanly.
So 13 would be...
Just 0.1 in base 3. Simple. But then fractions like 12 or 14, which are nice and finite in decimal, become repeating decimals. Or repeating trinimals, I guess, in base 3.
So the base really dictates which fractions terminate.
Exactly. And similar to how we use octal or hexadecimal as shorthand for long binary strings.
Right, grouping bits.
You can do that with ternary too. Base 9, sometimes called nonary, uses one digit to represent two ternary digits, or trits. And base 27, septemvidecimal, uses one digit for three trits.
Makes sense. Like bytes for binary, do they have a name for a group of trits?
Yeah, the term trits pops up sometimes, usually meaning a group of 6 trits, analogous to an 8-bit byte.
A trits, okay. So powers of 3 are fundamental to this really interesting efficient number system, but they seem to show up, well, everywhere else too.
They really do, and often the underlying reason seems to connect back to situations where you have 3 distinct choices or 3 possible states for each element or step in some process.
Okay, 3 choices, like where? Graph theory.
Yeah, they appear there. Sometimes in the bounds for certain problems, like the Moon-Moser bounds for maximal independent sets, or in analyzing algorithms. The Braun-Kerbosh algorithm for finding maximal clicks, its complexity is often related to 3 to the power of n3.
So the number of things you're counting, or the time it takes to find them, somehow involves powers of 3.
Right. And also, some very specific, highly symmetric graphs, certain strongly regular graphs, actually have a number of vertices that is a power of 3, like 81, 243, 729. These pop up.
Oh. Okay, what about combinatorics? That seems like a natural fit for this 3 choices idea.
Absolutely. The classic example is counting sign subsets.
All right.
If you have a set with n elements,
Okay.
for each element you have 3 options. Either you include it with a plus sign, you include it with a minus sign, or you don't include it at all.
Include positive, include negative, or exclude. 3 choices.
Exactly. So 3 choices for each of the n elements means there are 3 to the power of n total sign subsets.
That makes perfect sense.
And you see 3n counting other things too, like compositions of a number using only parts that are 0, 1, or 2, or certain kinds of walks-on graphs. Imagine walking on a triangle graph, maybe with loops at each vertex, allowing you to stay put.
So at each step, you could move left, move right, or stay.
Right. 3 options at each step. After n steps, you have 3n possible paths.
There it is again, 3 choices per step. What about geometry? I saw mentions of polytopes.
Yes, specifically centrally symmetric ones. There is a class called Hanner polytopes. Things like hypercubes are examples if you count all their faces, vertices, edges, 2D bases, etc., including the empty set and the whole polytope.
Yeah.
The total number of faces for a d-dimensional hypercube is 3 to the power of d.
Really? So for a square, D2, that's 3 squared, 9 faces.
That's right. 4 vertices, 4 edges, and the square itself makes 9. For a regular cube, D3, you get 3 cubed equal 27 faces.
Wow.
There's even something called Calais' third conjecture, which proposes that third is actually a lower bound on the number of faces for any essentially symmetric d-dimensional polytope.
That's a deep connection. And fractals. Powers of 3, or rather inverse powers, seem crucial there.
Oh, absolutely fundamental. Think about fractals like the Cauca snowflake or the Sierpinski carpet or triangle.
Yeah.
Their construction often involves repeatedly dividing something, a line, an area, into 3 parts, and then doing something with the middle part, like removing it or modifying it.
Like the Cantor set. You just keep taking out the middle third.
Exactly. And the Cantor set has this beautiful connection back to base 3. The points remaining in the Cantor set are precisely those numbers between 0 and 1 whose ternary representation can be written using only the digits 0 and 2.
No digit 1 allowed in base 3.
Right. So the geometry of the fractal directly reflects the base 3 structure of the numbers it contains. It's really elegant.
That is cool. Any other sort of fun appearances?
Well, in recreational math, 3n pops up as the number of possible configurations or states in the Tower of Hanoi puzzle with n disks.
Oh, yeah.
And that classic balance scale puzzle, where you have unknown weights and you're trying to identify them using a balance scale. If the scale has 3 outcomes, tilts left, tilts right, or balances.
3 outcomes per way.
Right. After W-weighings, you can distinguish between 3 to the power of 1 different possibilities for the weights.
Okay, that 3 choices, or 3 states idea, is definitely a strong theme running through all of this.
It really seems to be a core reason for its ubiquity. And even just within number theory itself, powers of 3 have interesting properties.
Like what?
Well, all powers of 3 greater than 1 are perfect totient numbers. That means if you repeatedly apply Euler's totient function and sum the results, you get the original number back.
Okay, that's a specific one.
And if you look at the sums you can make by adding distinct powers of 3, like 1, 1 plus 3, 4, 1 plus 9, 10, 3 plus 9 equals 12, 1 plus 3 plus 9, 13, and so on.
Yeah.
That sequence of sums, 1, 4, 10, 12, 13, forms something called a Stanley sequence, which has its own unique properties.
So it's not just the numbers themselves, but how they combine.
Exactly. Adds another layer. The OEIS entry is just full of these connections, interpretations involving coefficients of polynomials, specific types of colored compositions, all sorts.
Anything really weird?
There was one I thought was quite odd, 9, 27, 81, 243. This sequence itself apparently shows up as the sequence of possible interior angles measured in degrees of a simple polygon.
Wait, powers of 3 as angles in degrees in a polygon. That seems totally unrelated to the three choices thing.
I know. It just highlights how they can emerge from completely different mathematical structures sometimes. Really unexpected.
Speaking of unexpected,
Yeah.
let's talk about that puzzle from the sources, the one about concatenating digits. That really caught my eye.
Ah, yes, the concatenation puzzle. It's a great question. Can you take numbers from our sequence 1, 3, 9, 27, 81, and so on, and stick their decimal representations together, concatenate them in some order to make a new number that is also itself a power of 3?
Right, like the example they gave for powers of 2. You can take 1, 2, and 8, stick them together to make 128.
And 128 is 2 to the power of 7, so it works for powers of 2.
But is it possible for powers of 3? Like, could you stick 3 and 81 together to get 381? Is that a power of 3? No. Or 9 and 27 to get 927?
It sounds simple, but it seems really hard. You can use any powers, maybe multiple times, in any order.
Your first thought might be divisibility by 3, right? The sum of the digits rule.
Yeah, and any power of 3 except for 1 is divisible by 3. So it's digit sum to a multiple of 3.
So if you stick a bunch of them together, excluding the 1 perhaps, the concatenated number will also have digit summing to a multiple of 3.
Right. But that only tells you the result is a multiple of 3, not necessarily a power of 3. That's a much stronger condition. And if you include the 1, the digit sum rule gets more complicated anyway.
So has anyone found an example?
Apparently not, according to the sources. Computer searches have gone up to very large powers of 3, trying all sorts of combinations in base 10, and haven't found a single instance.
Huh. So maybe it's just impossible in base 10.
That seems to be the suspicion. But proving it's impossible is the really tricky part. It likely involves digging into the specific patterns of digits that appear in the decimal representations of powers of 3. They aren't random digits, right? There are underlying structures.
So it's an open question for base 10. But does it work in other bases?
Yes. This is where it gets really interesting. The sources mention that examples do exist in other bases, like base 8.
Base 8.
In base 8, the number 3 is just, 3, which is 3 to the power of 1.
Right.
Now, what happens if you concatenate 3 with itself in base 8? You write down the number 33 base 8.
Okay, 33 base 8. That's 3 times 8 to the 1 plus 3 times 8 to the 0, which is 24 plus 3, 27.
And 27 is?
3 to the power of 3. Wow.
Exactly. So concatenating 31 with 31 in base 8 gives you 33. The puzzle has a solution in base 8.
That's incredible. So the answer to the puzzle isn't just about the numbers 1, 3, 9, 27. It fundamentally depends on the base you're writing them in.
Precisely. The way the digits combine and interact is completely different in base 10 compared to base 8, at least for this specific property.
It really shows how a seemingly simple question about digits can connect number theory, different number bases, computation.
Yeah.
It's fascinating that it's easy in one base and maybe impossible in another.
It's a perfect example of that nerdy fun. A simple observation leading to surprisingly deep questions about structure.
Well, this has definitely been a deep dive into A000244. We went from the simple definition, powers of 3.
Explored its key role in the ternary system, base 3, with its interesting efficiency properties and history.
Then saw how 3n pops up all over mathematics, graph theory, combinatorics, often tied to that three choices idea.
Right through to fractals like the Cantor set, where it links back to the ternary representation, and even recreational puzzles.
And we finish with that really intriguing concatenation puzzle, maybe impossible in base 10, but solvable in other bases like 8. It really drives home the point about base representation mattering.
It certainly shows A000244 is much more than just a sequence. It's like a connecting thread, weaving through all these different mathematical ideas, revealing structures and sometimes real puzzles.
It gives you a great sense of the unexpected depth you can find just by looking closely at a sequence of integers.
And it leaves you wondering, doesn't it? Given how efficient base 3 is and how hard this concatenation problem seems to be in base 10, could there be some fundamental property about the decimal digits of powers of 3 that prevents this? Something specific to base 10?
Or does the answer lie purely in exploring different bases? And it makes you think, what other seemingly simple sequences in the OEIS are hiding equally complex stories and connections, just waiting for someone to take a deep dive?